All right, let's get right into it. Today, we're diving deep into the absolute beating heart of reliable systems by unpacking Chapter 8, Transactions, from the legendary book Designing Data-Intensive Applications. If you've ever found yourself wondering how modern apps manage to keep their data perfectly intact under massive, unpredictable pressure, well, you are in exactly the right place for this explainer. So let's set the stakes here. Imagine a highly anticipated concert, and there is literally one front row ticket left. Thousands of users hit buy at the exact same millisecond. How on earth does the database decide who actually gets that ticket? And, more importantly, how does it prevent the system from accidentally selling that single ticket to 50 different people? The answer to that lies in mastering the terrifying, yet kind of beautiful, chaos of database concurrency. Here is our roadmap for today. We'll start with the promise of ACID, move into the chaos of concurrency, cover snapshots and lost updates, then write skews and phantoms. After that, achieving true serialization, and finally, distributed transactions and 2PC. We are basically going to climb an escalator of complexity today, so let's jump in. Section 1, the promise of ACID. Because before we can appreciate the chaos, we really need to understand the ideal baseline that every database is furiously fighting to maintain. Transactions provide these fundamental safety guarantees, famously known by the acronym ACID. Now, a quick clarification here, atomicity in this context, it doesn't mean multi-threaded concurrency. Actually, scratch that standard definition. Here it means abortability. It's a strict all-or-nothing guarantee. If your network drops or a disk fills up halfway through some writes, atomicity ensures the database just tosses out that partial work so you can safely retry. Consistency means your data starts and ends in a valid state. Isolation ensures concurrent transactions don't step on each other's toes. And durability just means that once it's committed, it survives a hardware crash, for sure. But you might be wondering, why do we even need these complex multi-step transactions? Why not just modify one thing at a time and call it a day? Well, because real-world data is connected. If you have denormalized data, like, say, an unread email counter that absolutely must stay in sync with your actual unread emails, you have to group multiple writes together. Multi-object operations make sure that either both the counter and the email status update, or neither of them do. Section 2, the chaos of concurrency. What actually happens when things aren't just happening one by one in a nice, orderly line? Think back to our concert ticket scenario. What is physically happening inside the database when two users click at exactly the same time? It's not just a philosophical question, it's a mechanical one. Let's look at how this plays out on a timeline. Meet our first concurrency villain, the lost update. Imagine user 1 and user 2 both want to increment a counter, let's say from 42 to 43. They both read the value 42 at the exact same time. User 1 calculates 43 and writes it back, but simultaneously, user 2 also calculates 43 and writes it back. User 2's write completely clobbers user 1's write. We literally had two increments happen, but the counter only went up by one. The data is fundamentally corrupted, all because of a race condition. And it gets worse. Here's another nasty anomaly, dirty writes. So Aaliyah and Bryce are both trying to buy the same item. Aaliyah successfully updates the listings table to say she's the buyer. But before she can update the invoices table, Bryce's transaction swoops right in, overwrites her listing, and updates the invoice to his name. The rights just get totally mixed up. To fight this, databases rely on our first basic line of defense, the read-committed isolation level. This essentially uses row-level locks to prevent these uncommitted dirty writes from intermingling. Now, read-committed is great, but it definitely has its limits. Section 3, snapshots and lost updates. Because under real pressure, that basic isolation eventually fails us. When it fails, you get something called a read skew. Imagine Aaliyah has $1,000 total, split evenly across two bank accounts. She checks account 1, sees $500. Okay, great. Meanwhile, a background transaction transfers $100 from account 2 to account 1. Then, Aaliyah checks account 2 and sees $400. To her absolute horror, it looks like she only has $900 total. Her money seemingly vanished simply because she observed the database in an inconsistent mid-transfer state. To fix this, we bring in a hero called snapshot isolation. This essentially freezes time, guaranteeing that a read-only transaction sees a perfectly consistent snapshot of the database from the exact millisecond it started. So let's do a quick check-in on our progress here. We started at read uncommitted, which is practically the Wild West. Then we moved to read committed, using locks to defeat dirty reads and dirty writes. Then we leveled up to snapshot isolation, which defeats that read skew we just talked about. Notice that lost updates are still a maybe here. They often require atomic operations or explicit locks to fully prevent, but look closely at the bottom of the table. We still have some empty spaces to fill. And that brings us to the plot twist. Section 4, Write, Skews, and Phantoms. These are level 3 villains, and they can bypass even our trusty snapshot isolation. This is honestly one of the most fascinating bugs in software engineering, the write skew. Imagine a hospital system where at least one doctor must be on call at all times. Alia and Bryce are both on call, they both suddenly feel sick, and they concurrently hit the button on the app to go off duty. Alia's transaction checks the database. Are there at least 2 doctors on call? Yes, she and Bryce are, so she updates her status to false. But at the exact same time, Bryce's transaction asks the identical question, gets the identical yes, and updates his status to false. They both commit. Now, 0 doctors are on call. They made conflicting decisions based on the exact same outdated premise. So what actually caused that write skew? It's a tricky little phenomenon called a phantom. A phantom happens when a transaction searches for a condition, like how many doctors are on call, and makes a decision based on it. But right before the write is executed, another concurrent client changes that very condition. The premise of the query literally shifted right under their feet. Standard snapshot isolation cannot protect you from phantoms because the 2 transactions are modifying entirely different rows. To defeat phantoms and write skews, we have to bring out the big guns. Section 5, Achieving True Serializability. Serializability guarantees that even if transactions run concurrently, the end result is exactly as if they had run one by one, serially. There are 3 heavy-hitting approaches here. First, actual serial execution, literally just running everything on a single thread. It's blazing fast if your data fits in memory, but obviously it kills concurrency. Second, two-phase locking, or 2PL. This is a very pessimistic approach. It completely locks down ranges of rows so no one else can even breathe on them until you're done. Finally, we have serializable snapshot isolation, or SSI. This one is optimistic. It lets transactions run freely, but right before they commit, it checks to see if any premises changed. If they did, it aborts the transaction and forces a retry. Modern databases build the foundation for all these snapshot and serializable tricks using multi-version concurrency control, or MVCC, like we see here in Postgres. Notice how every single transaction gets a unique, ever-increasing ID, a TXID. When a transaction writes or deletes data, it doesn't just overwrite it in place, no way. It tags the rows with inserted by or deleted by transaction IDs. This is absolute genius, because it means readers never block writers and writers never block readers. If you're a long-running analytics query, you simply ignore any data inserted by a TXID that came after you started. You get a perfect, locked-in-time snapshot without slowing down the active system at all. But what happens when you outgrow a single database? Welcome to Section 6, Distributed Transactions and 2PC. We have reached the final boss. When your transaction needs to span across multiple different database nodes or even entirely different systems, you have to guarantee that either all of them commit or none of them do. This is solved by the two-phase commit, or 2PC, and it works like this. Phase 1 is the prepare phase. A central coordinator asks every single database node, are you absolutely 100% ready to commit this, and do you promise you won't crash? If even one node says no, the whole shebang aborts. But if they all say yes, we enter Phase 2, the commit phase, where the coordinator sends the point of no return order to finalize the writes. Now, this exposes a lingering, almost terrifying vulnerability of distributed systems, and I want to leave you with a provocative thought here. We just said that nodes promise to commit during the prepare phase, but what happens if the coordinator node itself goes down exactly between the prepare and commit phases? The other nodes are stuck. They are holding locks, entirely paralyzed, waiting in a state of doubt for instructions that might never come. Solving that incredibly steep cost of distributed commits is where the wild world of distributed consensus algorithms begins. But well, that is an explainer for another day. Thank you so much for exploring the fascinating world of database transactions with me. Stay curious, keep learning, and I'll catch you next time.